Hello, everyone. My name is Hamid Rajabi from University of California at Merced. Our paper is entitled MODES, which is Multi-Sensor Occupancy Data-Driven Estimation System for Smart Buildings. First of all, we want to look at the relationship between the buildings and energy. People spend 87% of their time inside buildings. That makes buildings an important part of our lives today. So in order to be comfortable inside buildings, we need to spend a significant amount of energy. As we can see here in these figures, in the United States alone, buildings account for 40% of total energy usage, out of which 50% goes to HVAC systems. Furthermore, more than 75% of occupants in commercial buildings are not satisfied with their thermal comfort. And that is due to the lack of information on occupancy and comfort. The occupancy is termed as where the occupants are and will be in the near future. And comfort is actually what they prefer while they are inside buildings. Therefore, we need a detailed occupancy information about the number of people in real time and in the near future for each zone, which allows us to conditioning zones for temperature only when they are occupied, and also adjusting ventilation rates based on the actual number of occupants. With the importance of occupancy information to control HVAC systems, there are several technologies on occupancy sensing and estimation, and you can see some of them here in this slide. However, having different occupancy estimates for different technologies, one approach could be the sensor fusion to take advantage of multiple of those technologies together in order to estimate the best occupancy. There are two sensor fusion techniques, early fusion and late fusion. The early fusion takes the raw signals from some environmental sensors, and then we will have a sensor fusion, actually a feature fusion and classification to deliver discretized occupancy values. The major issue with the early fusion, though, is that the majority of the occupancy sensors are black boxes and we don't have access to their raw signals. So this kind of techniques is mostly working in the academic environment, but in practice, when we have some black box commercial occupancy sensors, we have to fuse their final estimates only. That is the only available data we have from the sensors. In practice. And that is mainly why we picked the late fusion strategy in this study. In the late fusion strategy, as you can see here in this diagram, we let each individual occupancy sensor deliver its estimate, and then we fuse those estimates together and doing the classification to get a more refined occupancy estimate in the output. And this technique is the one we picked for this study. Here we see a whole picture of our work. Well, the MODES is a sensor fusion pipeline that takes two occupancy estimates from two different sensors, in this case, the thermal and vibration sensors. And then it applies some late fusion processings to merge those two occupancy estimates and refines that estimate through a particle filter to get the best possible occupancy estimate. And finally, we use this final estimate to do energy plus simulations and find out the energy and comfort, energy and like the quality of comfort effect, and then compare it with the result we got from each individual sensors, as well as with the ones of the late fusion and the particle filter modules. By the way, we picked these two sensors based on some criteria in the related work through comparison with other individual sensors. And you can see the details in the appendix of our paper. Now let's briefly introduce our two input sources. The first one is the thermal-based sensing system that is called ThermoSense. This system deployed on the ceiling and includes two sensors, one PIR sensor and one thermal array sensor. The PIR is in a binary selection form. It detects the movement of occupants and triggers the thermal array, which can count the number of occupants finally. And it consists of an 8 by 8 thermal array sensor that can cover an area of 2.5 by 2.5 meter. And the final output is the total number of occupants detected by the sensor. The second source is a vibration-based sensing system that is called Building Occupancy Estimation System, or BOES in acronyms. BOES, similar to the ThermoSense, is a non-intrusive occupancy monitoring system, and it captures vibration signals on the floor, then detects footstep events, and finally recognizes significant events based on observed walking traits. And the final output is the estimated occupancy count in the zone. And by the way, the covering area of the BOES is measured to be something between 2 and 4 feet radius from the sensor. Now, this is the modes pipeline here in this slide. Before we get into the sensor fusion module, each of those sensors perform some data-driven classification independently that is based on the raw signals they sense. And then each one outputs a discrete occupancy estimation values separately. Then we have our proposed sensor fusion module that is shown here inside this dashed blue curve. It consists of two submodules. The first one is the data-driven optimization-based weighted average, or DOA in acronyms. And it combines both occupancy estimates. The DOA's output is further refined by a particle filter, which uses a data-driven occupancy model that is blended Markov chain, or BMC, to further refine the occupancy estimation. This BMC, by the way, is already done in the literature, and it is not our contribution, but we are using it in this work. The final output of the process is a discrete value with more accurate occupancy estimation. The late sensor fusion process, or DOA in modes, is based on a weighted average between two occupancy estimates. Here we see the weighted average function. Each weight is defined as a quadratic function of the associated input data, and the optimal weights are obtained through a supervised layering problem. The optimal coefficient for each function are obtained through an optimization process that minimizes the least square error to the ground truth data. And there are some optimization constraints as well, like they should sum to 1, and each one is forced to have some values between 0 and 1. So makes two weights to be reciprocals. And the data requirements to converge to good parameter estimation are also explored and will be discussed later in the next few slides. This slide shows two examples of DOA's output as an intermediate data traces of the entire mode's sensor fusion process. Here we have two scenarios of high and low occupancy. The low occupancy includes up to 3 occupants during the entire time, and the high occupancy would be up to 8 occupants. In these two concrete examples, DOA assigns the thermal and vibration weights of 0.79 and 0.21 for high occupancy case, and 0.54 and 0.46 for the low occupancy case. The second submodule in the mode sensor fusion module is the particle filter, shown in this algorithm here. In general, it has 3 phases or 3 steps. First, we have the sampling from the occupancy model, which is BMC here. Then we have the calculation of the particle weights. The weights Actually, the weights are obtained from the measurement model, and the model is calculated from the distribution of the difference between the ground truth and the occupancy estimate from the sensor, which is the DOA's output in this case. One example of such a distribution based on our data is shown here in this histogram. And then the final step is the resampling, where we draw with replacement from the particle set, which is proportional to the weight. And then this new particle set is the desired one to determine the final occupancy of the room at each time step. Now, our experimental setup. We deployed 9 thermal and 4 vibration sensor modes in a university research lab, as you can see here in this picture. The lab area is about 51 meters square with 8 cubicles, 4 on each long side. And during the experimental days, the rooms start being occupied at around 10 a.m. in the morning, and the last occupants left the lab at around 5 p.m. And we recorded 14 days of weekday data, that is 11 days of low occupancy and 3 days of high occupancy. The thermal sensors were deployed on the ceiling, covering the entire lab. And one example of that is shown here in this picture. It can process the data locally and transmit an occupancy count with a low power 802.15.4 radio, which is aggregated in the backend server. The vibration sensor, though, were deployed at the entrance of the lab that acts as a vibration turnstile for all the occupants who are coming in or getting out of the lab. And they don't have wireless transceivers, and they were connected to the network with Ethernet cables. Here we have 2 examples of time series occupancy in 2 days for high occupancy on the left-hand side and the low occupancy on the right-hand side. The top figures on each side show the measured occupancy for both the thermal and vibration sensors and compare them with the ground truth value. The middle figures shows the the DOA corrected output, and finally the bottom figure shows the final mode's occupancy estimate. As we did see earlier, the DOA prevents the average from floating outside of the 2 sources ranges that is observed here in this box, where the vibration system is overcounting by 3 occupants. And then by adding the thermal source, which is more precise, the DOA provides an occupancy score with smaller overcounting, that is only 1 occupant. That is due to the degraded performance of the vibration system in detecting a larger group of people. Similarly, the thermal sensor gets overcounting in the range shown in this box in the left-hand side, where the vibration sensor undercounts, and DOA would again correct for that. And that can be explained by the thermal system overlapping in the sensing coverage. As it is clear in both scenarios, the overrun and counting cases have been corrected by the particle filter mostly, so it is fair to expect from the particle filter to deliver the best accuracy among all these data schemes. In this table, we see the classification accuracy, overcounting, and undercounting ratios for 4 different data schemes, like the vibration and thermal inputs, the DOA, and the final estimate of the mode system by the particle filter. We have also the ordinary least squares method, the OLS, as a state-of-the-art late sensor fusion method for comparison. And by the way, we applied the ridge regression to make the OLS more robust against inaccurate estimates in regression. The overcounting, or OCR, is defined as the ratio of the number of cases in which the estimated occupancy is strictly larger than the corresponding true case over the total number of examined cases. And the UCR has a similar definition, but for strictly smaller cases. The OCR and UCR metric are useful to determine if there is any bias in the occupancy estimator. It is also useful for the interpretation of the energy and quality of comfort analysis, and we will see that later. And in total, it is clear that the DOA outperforms the OLS, and also the final estimate of modes is improved over DOA. Considering a low accuracy of 0.33 for one of the sources, which is the vibration, we can claim that a final accuracy of 0.73 can be acceptable for a late fusion sensing module like the modes. Since in this work we have a multi-class classification problem, we evaluated the estimates based on the F score or F measure. Here's the definition of the F score. It is a function of the precision and recall or sensitivity. And the F score is a real value between 0 and 1, and the more closer to 1, the better precision and recall. The left-hand side figure here represent the entire behavior of multiple schemes in each occupancy class based on the F score metric for high occupancy cases. And the better performance of modes is clear in low occupancy classes here. And the left-hand side figure represents the corresponding confusion metrics of the modes for the high occupancy scenario. In general, the performance in lower occupancy counts, like the C1 and C2, outperforms the one in high or medium levels. And the reason for this behavior is in the pattern of each one of the sources. Now we have the accuracy of the modes as a function of total training data size in each scenario. The accuracy stability is reached with about 40% of total data in high occupancy cases. And we see that the low occupancy scenario can reach the stable accuracy level with a lower size of total data compared to the high occupancy case. And in the end, we have the energy analysis using the modes occupancy estimates. We split the analysis down to overcounting and undercounting scenarios. The figure in the these two figures actually show why we did over and undercounting separated analysis. The left-hand side picture shows the overcounting case, where we have zero occupancy in reality, but the system believes some occupancy. So this makes the HVAC system spending unnecessary energy, and we are actually wasting energy in this case. The right-hand side picture is the undercounting case, where there are some occupants in reality, while the system wrongly believes the room is empty. In this case, we may have some energy saving, but this will be at the expense of degrading the quality of comfort. This figure shows our simulation to show the effect of over and undercounting that we discussed in the previous slide. The figure shows the monthly energy consumption in two scenarios of OCR and UCR for 4 data schemes: the vibration and thermal sources, the DOA, and the modes. So based on our simulation and what was expected, the overcounting makes the system consuming much more energy compared to the undercounting case. Now, in this figure, we have the temperature effectiveness, which is an indicator of the quality of comfort. The figure shows like the product of room temperature, RMSC, and the number of occupants for 4 data schemes under over and under counting scenarios again. As we just discussed, the undercounting case degrades the quality of comfort, while in the overcounting, all the data schemes perform similarly with very lower RMSE values. And finally, this figure shows the simulation of annual CO2 concentration provided by each one of our data schemes in both over and undercounting scenarios. And it is clear that the mode's result is slightly like has a slightly like a lower concentration compared to the thermal and like the DOWAS output. Yeah, we were 6 people involved in this work, including 3 PhD students and 3 faculty members, all affiliated with the University of California at Merced. And in the end, we just want to summarize the topic. We picked 2 state-of-the-art occupancy sensors and did the extensive experiments to gather those data. We did the late fusion on their final estimates and refined that output by a particle filter. And finally, we did energy plus simulation to see its impact on energy usage and quality of comfort. And thank you so much for your attention and consideration. Thank you.